Chapter 6 is about thermodynamics. It's the movement of energy. So at the top, we have a table. We could have an open system, in which case matter and energy can flow in and out. A closed system, in which case the matter is trapped, the energy can flow in or out. And an isolated system, theoretically, where neither can flow in and out. I'll note, though, an isolated system, uh, no system is truly isolated. There we go. So this is a hypothetical, and I'm not quite sure why it's there, but there we go. No system can be truly insulated from its surroundings. So you can't absolutely trap energy. So we're going to talk about the calculation of energy, and the change in energy internal is equal to the heat plus the work. So Q is heat for some reason, and never really got told why. This is not related to the capital Q like with the KC math. This is completely different. Small q means heat. This is mass of the item, the substance being described. This is the specific heat, which I'll get to in a moment, and the change in temperature. Now, the change in temperature can be Kelvin or Celsius because the size of a degree in Celsius or Kelvin is the same. If you change 5 degrees Kelvin, that's also a change in 5 degrees Celsius. I realize the label will be different, but if you move from 0 Celsius to 5 Celsius, that's also a move of 5 Kelvin degrees. It's like they took the Celsius thermometer and just painted over the numbers. They didn't change the markings on the thermometer. The degrees are the same size. We usually use Celsius, although technically we could just use Kelvin in this here. So here's what it would look like. We would have Q equals the grams, because that's mass, and the specific heat. Now, here's the thing that's probably new, is the specific heat is how many joules, measuring energy, does it take to push 1 gram of this stuff up or down 1 degree Celsius? So you need a rating for the heat capacity. For how hard is this stuff to push around in temperature anyhow? And then this would be the change in degrees Celsius. Or again, you could have put Kelvin in either one of these and it would work just as well. Notice that the units cancel out to give joules, capital J. There was a Mr. Joule, and that's our standard unit of energy, or often said as heat. Really, it's energy though, because work can also be energy. And here's our work formula. Work is equal to negative sign times the pressure that you're fighting against. Usually that's on the outside of the system, like in our example down here, times the change in volume. So this is for working with a gas. So here's our little hypothetical. And we have a gas trapped in a cylinder under a piston. And let's assume, of course, that the piston is a constant weight. And so that exerts a constant force downward. So that means that when you fiddle around with this, like heating it up and cooling it down and so forth, the piston will move up and down because it will maintain a constant pressure in there. So this is a bunch of notes. This is kind of a big info dump. I would take a bunch of notes on all this stuff. For instance, water is 4.18 joules per gram degree C. Of course, that's in your table of constants and equations in the front of the test, but just maybe you need to recognize it when you see it so you just spot it faster. So if heat goes into this, if Q is greater than 0, if the energy, Q, of the system is going up, the change is a positive number, then that's endothermic. Endo inside, like you have an endoskeleton. So the therm, the heat, is going into the system if Q is positive, if it's greater than 0. And this is often written as delta H, like the delta H of the reaction or the system, the change in the system. And so that would be a positive. And we would rate it in kilojoules per mole, which we'll get into more later. And by the way, this is moles of reactions. If you run this reaction once, twice, 3 times, of course. Now, in reality, it's very easy to run this, no joke, a trillion times. That's not even remotely a problem in many cases. Of course, it depends on how much reactant you have. But running something a mole of times is usually not even that hard. So this is not moles of chemicals, it's moles of times the reaction happened. And so if we put work into the system, the work is greater than 0, that's a positive, and the energy would be going into the system. For instance, if we just grabbed this handle here and pushed, we would be working on the gas system. We're going to consider the gas as the system for this. And work would be going in, and we would be energizing the system because we're putting work into the gas. So work on the gas would be a positive number because work is going in, energy is going into the system. Well, if we did something, and this gas expanded, now what would it be? Well, it's a little hard to get gases to expand on their own without heating them. But anyway, if heat came out of a system, that would probably be a chemical reaction. So this is a little bit of an oddball for this, because can't think right now why heat would come out of this, why energy would come out of this on its own. But if energy comes out, then for the gas system, if energy is coming out, then it's losing energy. Okay, which means the Q, is less than zero. It's a negative number. And delta H would be a negative kilojoules per mole. And again, that's per mole of reactions. And so if work went out, like it pushed the piston up, then the work would go out of the system, like if it expanded. And again, I realize it wouldn't expand probably unless we heated it, but just pretend it magically expanded for a moment. Then work would be going out of it, and the energy in the system would be a negative number. And my example to the class has been, if you're opening a heavy fire door and you're fighting that big spring that's attached to it, work is going out of you, energy is leaving you. You get tired doing this because you're fighting against the spring. So work is going out of you, you're working on another system that's not yourself, and energy is leaving you. So also in a chemical reaction, if heat is going in, then what you're doing is you're creating more energetic chemical bonds. So for a chemical reaction, if we say it's endothermic, the chemical bonds are going up in energy. You're putting energy in, and not all of it comes out. Where did it go? It went into the chemical bonds. Bonds have very different energies depending on what they are. And so you can form bonds that are holding more energy than when you started. Well, if they're holding more energy than when they started, then energy has gone into the system and remained there. And so the overall energy has flowed into them. So if you run a reaction and heat comes out, which we're going to discuss on the other side of the paper, then the chemical bonds have released energy overall. Now they've also taken energy back in when they reform bonds, but overall, if energy comes out, then the chemical bond energies overall have gone down. And exothermic processes release energy, so temperatures tend to go up, which again we'll talk about more on the back. Exothermic processes tend to heat up their surroundings. The temperatures go up. So here's our example. We have a 20-gram sample of argon. That's a noble gas, so it won't react with anything. And we have a certain set of conditions. Hit pause and read that. So certain things are happening. What's the overall change in energy? Well, it's the change in the heat and the change in the work added together. Remember this up here? So let's find the values for each one. So it says it was heated, and it went from 30 degrees to 40 degrees Celsius. Now, the question comes up, which way do we subtract it? Well, if it's got heat increasing, then the energy went into the system. If we're heating the gas, then heat went into it, and the change needs to be a positive value because the change has increased, the heat has increased in the system. So we know we got to get a positive joule number here. So let's subtract this such that we get a positive number, because when we multiply this, we got to get a positive answer. So it's the 20 grams that they told us. Here's the specific heat that they told us. And here's the change in temperature, and we got to have a positive number. And when we multiply them, we get a positive 104 joules. So for the work, we have negative of the pressure that we're fighting times the change in volume. Now the change in volume was a positive because it went from smaller to bigger. So we're going to subtract such that we get a positive number, because that's what we need to know. We need to know, did it get bigger or smaller? So it expanded into the outside against the pressure from the outside. Remember, the pressure from the outside was that amount. and that's in kilopascals, which I can discuss in a bit. A pascal is your standard unit of pressure in science. There are some other things that you hear about, like pounds per square inch and stuff, at least in North America. But a pascal is what you need if you want to do science units. Now, here's the thing: if you do work that expanded positively, got bigger, then did the energy of the system go up or down? Well, if you did work by expanding this against the pressure, then the energy of the system went down. And that's why we've got a negative here. So we know that we need a negative answer by fighting outward against the pressure. And so we know that we need a negative answer. And that means this has got to be a positive subtraction answer so that in the end, when we multiply by the negative, we get a negative answer for joules. So we're going to subtract to get a positive number, multiplied by the pressure that we're fighting against, slapped a negative on it. And that gives us a kilopascal liter. And it turns out, I'm going to skip the rest of this because it won't help on the test, but it turns out that a kilopascal liter is a joule. And I actually stepped my way through it. If you really want to hit pause and go through that, I found a page explaining it, but it is a kilopascal liter is really a joule. It's another statement of the same thing. So when we get that, we can just convert it in our minds and just say, well, that's the same number of joules, because really a kilopascal liter is a joule. So we can just call that joules, and we get a negative answer there because we lost energy by doing the work against the outside. So the total change of energy internal is Q plus W. So we're just going to take these two and add them together. And there's our overall change. So it loses 87 joules of energy to the surroundings. So a pascal is 1 Newton of force per meter squared, and that's really small. You may not have much experience with newtons, but over a square meter, visualize a meter stick left and right, and then to and fro, and that's a square meter. And 1 Newton spread all across a 1 meter squared is such a low number that right now, as you hear this, you're living in about 100,000 pascals of air pressure. So you can see that a pascal is not very much pressure at all. And in real Earth human situations, we generally end up dealing with kilopascals. So here's an example about chemical bonds breaking and so forth in exothermic and endothermic. So we dissolve sodium hydroxide in 100 milliliters of distilled water, and the temperature goes up. So what do we know about that? Right away, if I know that the temperature of the water went up, well, that didn't happen by magic. And it may be tempting to think that the heat was manufactured or created, even worse, so to speak. And I'm going to argue against both those terms. It was released. Released from what? Well, it was released from the chemical bonds that were existed before. So we broke some bonds, we formed some bonds, then we'll talk about those. And overall, energy came out. Energy came out of the process of dissolving this. Otherwise, why did the water get hot? The energy came from somewhere, and it's not magic. It came from the process of the dissolving. So that process is exothermic with respect to the process there. So what's happening when this is heating up? Well, let's go back to a note on the front. That temperature is the average kinetic energy, often written as Ke, like this. And kinetic energy is 1/2 the mass times the velocity squared of the substance. Now, I don't even remember if that's in the reference pages of the test, and it's not that important because they don't ask this as a calculation, but they do think you know the general idea. So if we have a system of water, the mass of the water is not going to go up because all the water is trapped in the bag. We know the temperature went up, and the temperature is defined as the average kinetic means moving, energy. Okay, well, if it turns out that energy of movement, kinetics, is 1/2 mv squared, and the m can't change, what happened? This went up and the m can't change. The velocity must have increased. So another note for self is temperature going up is faster molecules, temperature going down is slower molecules. So what happened when we dissolved the NaOH? Now we had a crystal of it. It says it was a solid and it's dissolving. So we have plus minus, plus minus, plus minus. We have the NaOH minus, NaOH minus, and so forth. So we're going to have to do a few things here to get this dissolved. Now, at least to some extent, this stuff was pretty happy being a crystal, a solid. Otherwise, it would have broken apart already, right? It must be some level of stable. Otherwise, it would already be changed. So we're going to give it an opportunity to change. But like I said, it's some version of stable. We're going to have to put energy in to breaking the NaOH bonds, ionic bonds. This is endothermic. Energy is going in to break up the bonds to tear this up into bits. Also, what do we get? Now, when we tear this up, we get them surrounded by water. Look, they're dissolved. They're floating around in water individually. Now, the water didn't exist like this before. The water was like this with its little hydrogens, their partial pluses, right, pointing at the minuses of its little neighbors. Because your intro class should have covered how water is really polar and it forms hydrogen bonding also. And the hydrogen pluses point at the minuses of its neighbors and vice versa. And this just continues on by billions and trillions and trillions and trillions and trillions. So the water was pretty happy floating around with its little pluses pointed at its little minuses because plus attracts minus. And we're going to change that because if we're going to shove a plus ion in there, what's going to happen is these things are going to stop being oriented like this to its neighbors and they're going to be very attracted to this total plus, not a partial plus, but a real positive ion. And it's going to flip all these around here in a sphere, really, of course, not just in a circle, with all the oxygens pointed at the positive ion because the oxygens are a partial minus. So what we're going to have to do is change it from this situation to that one. And so again, this was some version of stable. Otherwise, why was it doing that? So it likes to be like this. That's why it was doing it, of course. We're going to have to put in energy. That's an endothermic process putting in energy to break the hydrogen bonding so that we can go from this situation to that one or this one. Okay, so we've broken this up into little one ion bits, singles by the billions and trillions, and we've gotten these to quit just nose to tailing like this, and they're going to do this. Okay, now they're going to settle in. Now, obviously, this is attractive. That's why they're doing it. And another way to say attractive for nature is energy releasing, and I would write that down. Why does nature do something in some chemical reaction, some orientation? Because it's the most energy releasing thing it could find at the moment. And that becomes really key here, and I would write that down. And that makes it stable. When it releases energy, it creates more stability. And why did it do a thing? Create a reaction, create certain bonds, and so forth. That's because it was the biggest amount of energy release it could find at the moment. And nature wants to release energy and create entropy, which is going to come up. And entropy, that's a Y at the end. Entropy is chaos. It's disorder. And we'll get deeper into that later. So we put in energy to break up the crystal. We put in energy to get these guys to quit just hugging their neighbors. And then they're going to all flip around and get attracted to this. Now, when it did that, like I said, it's releasing energy. That's why nature does it. It's the biggest release of energy it could find at the time. And that's exothermic, releasing energy. Energy is going out. And then we have the OH minuses. And of course, that's also a release of energy, same kind of idea, except for a negative, the hydrogen sides are going to point at the negative side. And just as a bit of a sidebar, the test really does think you know that, and it really is on the table to be asked. They think you know a water molecule when they diagram it, kind of like this. Of course, it's not dark and white. That's not the point. It's big and small, sort of a little Mickey Mouse head here, that kind of thing. And they think you know that the oxygen is minus and the hydrogens are plus. So I would write that down. And they also think that you know that if that's a plus, then the negative oxygens are going to orient toward it. If that's a negative, then the positive hydrogens are going to orient toward it. And that could really be a multiple choice question. So they might ask, which of the following is the correct orientations? And they have this one. And then they have one where it's always the oxygen's inward, which would be wrong here. One where all the uh, water molecules are the hydrogens in, and that's wrong for this one. And then one where they're backward. And that would be 4 choices. Here's a really good diagram. I like this. So we put in energy to do step 1, say that NaOH, breaking up. Step 2, breaking up the water to quit just hugging its neighbors. And then it started settling in. And so it made bonds with one of the ions and bonds with another ion. And remember, I said it settles in because that's the biggest release of energy it could find at the moment. And it turns out that it released more than it gained. So overall, that's a loss. That's why the water went up in temperature, because energy was released from this reaction. And so this part is endothermic, just this part. This part is exothermic. And so the whole thing overall is exothermic. I meant just this part is endothermic. These 2 steps are endothermic. So what's the heat flow for this process? Well, it's Q equals mc delta T. So the M of the water, they told us, this is just a fact of water. You can go look it up. And the change in the temperature, again, was supposed to be a positive. So we're going to do big minus small so we get a positive, because we know that the energy into the system was a positive. So from the water's perspective, that was a positive inflow, right? So we need to get a positive number. So this subtraction needs to give a positive number. And then we can multiply it out and get the joules. So what's the calculation for the delta H dissociation? So this is change. Capital H here is not hydrogen. It is heat. It is energy. And that's dissociation. That means for this to come apart and then get dissolved. So the heat for reaction, Rxn is reaction, is the negative of whatever happened to the water. Because where did the heat come from? It came from the reaction. Where did it go? It went into the water. So we said from the water's point of view, the change is positive, right? But from the reaction's point of view, the change is negative. The water gained the heat, the reaction lost the heat. So if we're going to talk about the heat of reaction, it's actually a negative. And we've said many times already that this was an exothermic process. The dissolving process was exothermic, and that's a loss of energy, a negative amount of joules. However, there is something else to say, that delta H is usually rated in kilojoules per mole. That's not mole of chemicals, and this is a little hard to make sure everybody gets straight. We are not talking about moles of chemicals or atoms or molecules. Remember that a mole is a number like a dozen is a number, and I can run this reaction once, twice, 3 times, a dozen times, 100 times, a million times. I can run it a mole of times. We can have a mole of times that the reaction happened. And that's what we mean. It's a kilojoules that will happen if you run the reaction a mole of times. Well, let's see here. So I need a mole of reactions. Now we happen to know that for every 1 mole of this, we get 1 mole of reactions, don't we? For every one of these, we only get this happening 1 time. Now, that may seem so obvious that it's not worth mentioning, but it is worth mentioning, because just for a moment, let's pretend that there was a 3 here. Then the number of reactions would only be 1/3 as many moles as I had here, because 3 of these will only get me 1 reaction. So if I had 300 of these, I can only run the reaction 100 times. If that's a 3, let's pretend, then the number of reactions is 1/3 as whatever the moles of this is. So if I find out I have 6 moles of this, I can only run the reaction 2 moles of times. So how many moles of NaOH do I have? Well, let's find the molar mass and divide, and that's the moles of the NaOH. This I find a little confusing, but here's the conversion between the NaOH and the moles of reaction. It's 1 to 1. And here's the joules. And what we're going to do is then take the joules per the moles of reaction. So what I personally would do is I would say that this moles, and then do this, and I get actually with this flipped, and I get moles of reaction. And of course, I know it's just the same number in this case, right? So I'm going to run at 0.25 moles of times, and I'm going to take that number and put it under the joules, which gives me here 4,440 joules per moles of reaction. Now, usually, again, though, this is rated in kilojoules. So when I divide by 1,000 to get kilojoules, it's 4.44 kilojoules per mole. And that's what was happening here when we divide by 1,000 to turn it into kilojoules. This was my note because of the misprint from the previous statement. So we're going to ignore that for now. That's wrong. I fixed it.